You posted this really nice, or you retweeted that really nice sort of flow chart on Twitter, where it's a very basic thing. It's like orbital changes and feedbacks lead to further release of carbon dioxide. So I'm going from the direction of coming out of an ice age, but orbital changes.
We're for sure gonna die to
crap.
this storm.
Yeah, we were just talking and just running around.
I think didn't we see a rift somewhere?
I have a porta rift. Can you guys jump
Oh,
into
yeah,
this?
I'm coming.
Okay.
All right. Just
Brian,
go, just go, just go.
I
don't know if we have time.
Okay.
Oh, yeah.
Brian. Jump in this thing.
Yeah.
Jump
Go.
All right, press the space button, or whatever the button is to deploy.
Oh my gosh.
I didn't know multiple people could jump into it.
Yeah, it lasts for like a second, so I don't. It looks like Brian might not have made it.
Sorry, Brian.
Oh man. We might still be in trouble here. Isn't there usually a bunch of rifts? Oh, there are, right by the hamburger.
Up here?
Yeah. Oh my gosh, I think we're gonna make it. Intro.
Yeah.
All right. Welcome, Riley and Brian, to the Climate Fortnite squad. We're here doing some squads, and we're going to talk about ice ages and how they relate to modern global warming. And we're going to go to Haunted Hills, get real far away. So, Brian, in a few seconds, you're going to press, well, I don't know, whatever the button is for you to jump, and then as soon as you fall out of the thing, you're going to hit the button so that you float.
Okay.
So do that now.
Okay, here we go.
And press the button again so you get the glider out.
Okay.
And turn hard to your right.
Yeah, and you're gonna, turn like a 90 degrees to the right. All right, perfect. All right, so I'm Henri Drake. I'm a MIT climate scientist grad student. So I've been here for 3 years now, and I'm generally interested in all things climate modeling and climate change. But my dissertation topic will be looking at the circulation of the very deep ocean, so basically the bottom half of the ocean, so the bottom mile or so. So how about you, Riley? Do you want to give a quick intro?
Yeah. So I'm Riley Brady. I'm a PhD student at the University of Colorado in Boulder, studying atmospheric and oceanic science, and my main focus of interest is on ocean chemistry. So I work also mainly with climate models, but recently I've been interested in how climate variability and climate change impacts things like carbon fluxes into and out of the ocean from the atmosphere.
Cool. How about you, Brian? Do you want to give a quick intro?
Yeah, sure. I'm Brian Kahn. I'm a journalist with EARTHER, which is a Gizmodo media site. I also teach in the Masters in Climate Society program at Columbia, which I did now, embarrassingly enough, 10 years ago. And this is my first time playing Fortnite, so I'm hopefully not to embarrass myself too bad there.
Cool. All right, so really quick, how long has the climate communications program been at Columbia? So we've already had a couple current students on for our show.
Yeah, I know. It's like I'm following their footsteps, albeit I'll probably do it more poorly than they will in Fortnite playing. We've been around for, I think, 14, 15 years now, so I was semi-early to the program.
Cool. All right, so I think the plan is to talk about ice ages, and I thought a good place to start is basically talk about what they are. So just as a quick review, ice ages are basically this period. So the most recent one was about 15,000 years ago, where basically all of North America and the Arctic was just completely covered in ice. The world was a lot colder. Carbon dioxide concentrations were half of what they are today. And it basically, that didn't only happen 15,000 years ago. It also happened 115,000 years ago, and about 200,000, 15,000 years ago, 315,000 years ago. So it happens basically every 100,000 years or so. And it's done that for the last million years. And most of the time in between these ice ages is, or some of the time between these ice ages is basically this interglacial period, which is sort of a similar climate to today. So it's a lot warmer. There's basically no ice over, the United States. And just to give a little sense of how much ice we're talking about during these ice ages, where I live in Boston was under like a mile of ice. So, think of how tall the buildings in most of the big cities in the US are, and like several times that height of ice just totally stacked on top of the continent. So yeah, that's basically what ice ages are. I don't know. Do you guys have anything to add about ice ages or something cool you've heard about them?
In terms of the definition, I think one of the interesting things is we hear ice ages and we think about, this planet covered with a gnarly amount of ice. But I guess by definition standards, we're still in an ice age today just by the virtue that we have glaciers, ice-covered poles.
Okay. Yeah, so I think there's a little bit, some people rightfully get this very confused, and I did too. So I'm being a little loose with the definition. So ice ages,
Sure.
they are anytime you have an ice cap on the poles, but then within ice ages, there are these glacial states where there's really, very
With full
advanced
glacial
glaciers.
coverage.
And then there's these interglacial states where there might still be some ice, but it's significantly reduced. And so that's the cycle. Like you're always in an ice age for the last million years, but you cycle between sort of this very glacial state and a less glacial state. And then when you go back really far, like a million years, then you have millions of years without any glaciers at all, and these very warm climates. Maybe we can talk about those a little bit later too.
Yeah.
So I think one of the things that I think is really interesting that I feel like probably most people don't know about this. I certainly didn't until I took some classes. All right, we should probably start heading to this zone over here.
The Brian, just head to the giant circle.
Okay.
Actually, here, do even better than that. Go up this ramp, and
All
then
right.
you'll see it when you start walking towards this way. And I have a
All
jump pad.
Okay, let's see if I can get my lady turned around here. This is so funny using this on mobile. It's like, all right.
Yeah, I haven't tried mobile. I imagine it's difficult.
It's a little change of pace. It's a little different. I mean, then I've never played with not mobile, so who knows?
It's true. You have no baseline.
Oh man, I just fell. But yeah, so something I feel like most people don't realize about ice ages, and especially the difference between the glacial and the interglacial parts of ice stages, is that a lot of the warming that gets you from a world where the U.S. is completely covered in ice and a world similar to today is basically CO2. And it's not CO2 that's emitted by humans. It's CO2 that's basically mostly emitted by the oceans. Riley, do you want to talk a bit about how some of that chemistry works out?
Yeah, sure. I guess one point to make is that you're placing that on top of the orbital cycles. Do you want to go there after this?
Yeah, I guess maybe I should start with the orbital cycles.
Yeah, I'm happy to talk about carbon.
Yeah, that makes sense.
Because that kind of modulates the orbital cycle effect.
Yeah, so the way that these ice ages really work, at least as far as we understand today, some of this is still active research, is that the orbit of the Earth around the sun actually changes. And it's not so much that the Earth gets closer or further from the sun. That's only a really small change and doesn't account for very much warming at all. It's that basically the axial tilt of the Earth towards the sun changes. So the seasons change. So in certain parts of the climate, summers in Antarctica or summers in the northern hemisphere are closer to this, they're pointed more towards the sun. And so you're not really changing sort of the amount of solar radiation that the whole planet gets over the year, but you're changing how much the poles do. And that can have a huge effect because of these feedbacks that we're about to talk about. So maybe I'll start with the other feedback, the other major feedback, which is the ice albedo effect.
Yeah, it's great.
So this is basically the fact that if you change how much solar radiation the poles get during the summer, you're going to change how much ice melts during that summer. And so if you are melting less ice, then you have basically less ice just covering the surface of the Earth. And ice is really interesting in the climate system because it's one of the most reflective things we have on this planet. So it reflects something like 90 or 95%, depending on how dirty it is. It reflects 90 or 95% of the incoming solar radiation. And so, oh no, Brian, we're losing you.
I know, I'm gonna make it. Sorry, I'm like listening. I was like,
It's okay. We'll get you next game.
all right.
Now you can talk without having to run around and bash stuff.
Yeah.
No, I cannot think. I cannot think about this game anyways.
And so where was I? Oh yeah, the ice albedo effect. So if you have less of this reflecting ice covering the surface, you're just going to get more solar radiation coming into the planet and being absorbed. and that's basically going to warm the planet even further than the well, it's going to warm the planet in the first place. And then there are other feedbacks. So do you want to talk about those? So once you've done the orbital changes
Sure.
and you've done this ice albedo effect, you've warmed the planet a little bit, but not enough to get all the way out of the ice age.
Yeah, so I mean that's really interesting. I think a lot of people, when they think about ice ages, they first think about those Milankovitch cycles you're talking about. So, you know, these 20,000 to 100,000 year changes in orbital parameters, you know, the tilt and how it rotates. But that doesn't get you all the way there, and neither does the ice albedo effect. So you have to account for carbon dioxide, and this is from a natural perspective. So this is the carbon dioxide cycle completely void of human influence. And it's a complex system. So starting, for instance, in terms of a pure ice age, we look at sort of, well, first off, I guess with the carbon cycle, we think of a few reservoirs for that carbon, and the main ones are the atmosphere, the ocean, and the land. And during an ice age, you get a lot less, you know, vegetation and biology on the land. So you have ice covering surfaces, you have more deserts, so you don't have stuff growing as much. And by just taking away those trees that tend to store carbon, that land during an ice age actually acts as an input of carbon to the atmosphere. So, like you said way earlier, when we think of an ice age having a ton less CO2, so, you know, something like 180 parts per million, 280 parts per million during interglacial time, the land actually acts as a source. So we have to account for something else to take away a lot of that carbon, and that's the ocean.
We got a squad right ahead of us.
All right, let's deal with these guys.
I have faith in you guys.
I've never been in the zone, so I'm not used to jumping up like this.
Yeah, I know. I think there's just one guy up here, actually, so hopefully it won't be too hard to kill.
Wow. I got one shot at him. He's got,
he's got a trap in there?
He set up a trap, yeah.
Yeah. Oh no, I fell down.
Oh, this is crazy. These mechanics are kind of
Oh,
hard.
we got another guy here.
Is he down there with you?
Yeah.
Got him.
Nice. Got another one ahead.
Ooh, oh, another one right here. Ah, I'm down.
Oh, wait. Oh, I'm probably gonna be down here. Yeah. Oh well.
That was tough. Let's not go back into the zero gravity zone.
Yeah. All right. Oh, hopefully
Cool.
Brian.
Not bad. So you want me to continue? We get back in the game just because I'll get cut off by the loading screen.
You can just start now. I think it'll take a while for Brian to realize he has to hit leave lobby.
Okay. Yeah. So I kind of left off talking about the terrestrial carbon source during an ice age. So that actually adds carbon to the atmosphere. So in terms of trying to find where all that extra carbon goes, we turn to the ocean. And ocean carbonate chemistry is really complex, and that's why I find it fascinating.
Yeah.
And,
that's why I like to collaborate with people who find it fascinating.
Sorry, let me revise that. I got forced to find it fascinating by my advisor, and it's one of those things that over time I learned to find it fascinating. You know, what's that effect when you're start to enjoy your captive?
Oh, the Stanford prisoner thing? Is that?
Yeah, sure. Yeah.
Yeah, I forget what the actual Stockholm effect is. That it? I don't know.
Stockholm, that's it. Yeah, I have Stockholm syndrome with ocean chemistry.
All right, quick interjection. There's a.
Sure.
I have a set of notes from Ellie Zipperman at Harvard, which is titled
Yeah.
"How I Learned to." What was it? You know the that movie about the nukes? What's that called again?
Maybe the nukes.
I don't know. Anyways, it's called like something like "How I Learned to Forget and Love the Ocean Carbonate Cycle" or something, and it's a play on some movie from like the 60s or 70s or something.
Okay, I'm gonna write that down. I get some paper here. It's Ellie What's his name? Zipperman?
Yeah, Ellie Zipperman. I'll find those notes and send them to you.
It's funny. Oh, looks like he's back.
All right. Hey, Brian. No, not yet.
His little microphone thing's red.
Yeah. Oh no. He's probably still in the loading screen or something. I wouldn't be surprised if the loading screen takes longer in mobile.
Yeah, I'm just surprised the. Oh, there we go.
All right.
You ready for another one?
I think so. Yeah.
All right.
That drop was perfect. I mean,
Yeah, you did.
we,
You did a good job.
we
First-
still placed in the, there's like 30 people left and we only had one battle, so.
All right. I moved to the
Um,
right place.
So next time when we all die, you can just hit. Should be a button for like releasing from the lobby.
Yeah, got it.
Okay, cool.
Yeah, we figured you were stuck in there.
I was stuck, and then it was like, I was learning. There's a nice little screen that comes up that tells you like what does what. I'm like, oh, all right, cool.
Oh, cool. Nice. I'll just continue when we get in there because I think I'm gonna get cut by this loading screen.
You want to hit ready, Brian?
Yep.
Cool.
All right, that wasn't bad. We got.
Yeah.
Let me see what.
Did we get any eliminations? I don't think so. Or we
No,
knocked
no.
some people,
Oh,
but
no,
I
I
think
got
they
one.
revived them. Yeah. All right.
Okay.
Did we lose Brent? He'll come in hopefully. Yeah, there he is. All right. You wanna continue with your
Sure.
tutorial of ocean carbonate chemistry? This is like actually gonna be useful studying material for me because
Okay, cool.
I've like tried to
So-
understand this stuff, but it's just so complicated.
Well, dude, to be honest, like carbonate chemistry becomes a field of heuristics, and you just learn how things change, and you can sort of develop an intuition, but there's a bunch of different approaches you can make, and it's
Okay.
because like the carbonate system, for instance, is a system of 10 equations, and they're all
Yeah.
coupled together. So you have to solve them via some equation solver. And so long as you have two variables, so if you have something like PCO2 and alkalinity, you can solve the rest of the system, but it's not immediately intuitive. So
Yeah.
you start to learn, like, I work mainly with PCO2 and CO2 flux, and you start to learn, like, when temperature goes like this, when temperature warms, PCO2 goes up, and the salt, when it gets saltier, the PCO2 goes up. When it becomes more alkaline, it goes down, and so
You're out.
you
Yeah, I
just
see.
learn heuristics. But yeah, so to continue, I guess. Yeah, so we look at the ocean as this sort of missing sink for a lot of the Ice Age carbon, and I guess one way to look at it is there's a lot of different sort of systems in place to sink carbon in the ocean, and the one you're probably most familiar with and work with is the solubility pump, the physical pump of CO2. So I guess one way to account for CO2 dissolving into the oceans during an ice age is the fact that the oceans were on average a few degrees colder. I mean, at most they can only be, 3 or 4 degrees colder because the abyssal ocean temperature is like 2 or 3 degrees, and you can't go below -2 or you're gonna freeze it. So
And just to clarify, the reason you can't go below -2 rather than 0 is because it's really salty, and so that brings down
exactly. Good point.
freezing
Yeah.
temperature.
So if we just like if you just take that as a metric and say, okay, let's say the Earth cooled 3 or 4 degrees, then colder seawater takes up a lot more CO2, and that's just for any gas. A colder fluid takes up more of that gas, be it oxygen, carbon. And even with those colder temperatures, it only takes up so again, we're looking for that missing sink of like 100 parts per million, and that solubility affects only like 20 parts per million.
Yeah.
And then back to what I said earlier, when the ocean's saltier, it actually, the solubility goes down. So the ice age, because a lot of the fresh water was stored in ice caps, the ocean by virtue was saltier. So it's colder but saltier, so actually that saltiness is releasing some of the carbon. So the physical effect really doesn't account for us having way less carbon dioxide during the ice age. So we looked at the ocean as a missing sink, and then we say, okay, is it physics? Well, only a little bit. So you actually have to say, what else controls the levels of carbon dioxide in the ocean? And the answer is biology. So
that's a potential answer. I'll have you know that my advisor has a different answer.
Sure. This is not, to clarify, this is not my field of expertise, but this is one potential answer, and I'd like to hear your advisor's.
Yeah, I'll get to it.
Sure. But I guess in a broad scale, in review papers, one of the leading hypotheses is that biology plays. And with biology, in terms of carbonate chemistry, we think of sort of two major ways of biology sinking atmospheric carbon in the ocean. And one of those is what we call the soft tissue pump. And so that's just, you have phytoplankton that are growing in the ocean, and they ingest atmospheric carbon and convert it into organic matter bodies. and that organic CO2, when they die, sinks the ocean depth. A lot of it gets grazed upon in the surface layer, and bacteria also convert it back to CO2. Break down the organic matter, and but a small fraction of it drops below the mixed layer, so the upper ocean, and we consider it sequestered into the deep ocean. So that's that soft tissue pump. And then we also have the hard tissue pump, and that's these shell-forming organisms. So some phytoplankton form shells, just as corals do, and so those guys sink a lot faster with these calcium carbonate shells. And the big player here on long time scales is those calcium carbonate shells dissolve into the ocean sediments and sequester carbon for a long time. So I guess, yeah, one of the hypotheses is that ocean biology played a major factor here, and the notion is that biological pump is more active in the global oceans, and that's, be it more active. I guess the leading hypothesis would be is that it was more active holes in the Southern Ocean.
Yeah.
In the Arctic. But yeah, one point I missed, I guess, also from a physics perspective, I was just talking about the solubility pump, but from another kind of indirect physical impact, we think of the Southern Ocean as near the ice edge, this big upwelling cell. So basically, you have these eastward flowing winds right near the Antarctic continent, and because of the rotation of the Earth and friction, this tends to push water northward towards the equator, and that water is replenished by what we call upwelling of waters below. And those waters are really old, so they're bringing up really deep, really old waters that are just chock full of carbon, because they naturally have carbon from the atmosphere, but they also had those plankton dissolved into them. And I guess one hypothesis with the Southern Ocean is that in a colder climate, that the eastward heading winds would shift more towards the equator and reduce that upwelling. So you're actually reducing the outgassing limb of carbon from the. There's a lot of sort of factors at play in terms of carbon dioxide effect, but by removing it from the atmosphere via the ocean in terms of physics and biology, you're going to reduce the radiative effect of greenhouse effect of carbon dioxide, and thus add more cooling onto that ice albedo effect, also add more cooling.
Yeah, so I think the stuff you were just saying about the like winds, the winds changing, and that causing less upwelling is pretty similar. Okay, we have a fight here. Where's the
All right.
Oh, yep. All right, let's put this on pause.
All right. I got a lot of. Oh man. I got a lot of hits on him, but there's 3 of them.
Yeah, there's too many.
It's tough to keep your process of thought going while you're running around mining and then people show up.
Yeah. I'll get back to what I was talking about once we get back into the game.
Okay, but it sounds like the Southern Ocean limb stuff is what you're referring to.
Yeah, it's just instead of the winds, it's sea ice basically blocking off the lower limb. So the like waters that I'm talking about right now, the Antarctic bottom waters, you basically increase the volume of those by a shift in the sea ice edge. And the sea ice, basically there's very little CO2 flux out of there.
Yeah, you basically cap the air CO2 flux with ice.
Yeah, and so if you
Just a minor
increase
amount, but-
the amount of volume capped by that, then you can sequester more CO2. That's the basic idea. All right, so we probably have almost enough material for like a video, but Brian, you haven't contributed much, so is there anything you wanted to add to the conversation, or?
I mean, I'm kind of like here. I'm here to listen and learn from you guys and from Fortnite killing me repeatedly. But yeah, I mean, I don't know. I mean, I'm just happy to keep listening. But if you want me to if something like you want me to say, I'm happy to chime in.
No, I just wasn't sure if you were aching to say something and just were too distracted by the game.
No, I'm like very distracted by the game, and very much trying to be like, where am I going, and am I still alive? I think I figured out how to like jump at least. So
oh, great.
Yeah, so I mean that's about the base of my knowledge with ice ages and linking it to carbon. So I think it would be good for Henri, for you to talk about maybe the Southern Ocean effect, and then maybe the three of us can talk about how it relates to modern day climate
Yeah,
change.
that sounds great. All right, let's get back in the game then.
Cool.
Sweet.
I got to think about the modern links. I mean, there's a lot of places you can sort of discuss it.
Yeah.
More of a transition out of the ice age, the opposite effects that we're talking about.
Yeah, I was just thinking, like on a very basic level, most of the warming that got us out of the ice age, they get you out of, well,
All right.
yeah, I was
Last
thinking,
thing I heard, most of the warming that got us out of the ice age.
yeah, so most of the warming that got us out of the ice age was due to the CO2 effect, and that was just from 100 ppm of CO2, and so so CO2 relates to warming, or at least the warming effect logarithmically, so increasing by another 200 ppm, which we'll probably be at in the next 20-30 years, I would guess. You can sort of expect that would give a similar amount of warming. And so if you're going from having a 1 mile block of ice, a 1 mile thick block of ice over all of northern US, to having no ice there, then you can sort of imagine the magnitude of the changes we're going to have by the end of the century. And there are big uncertainties on those numbers, but at least you're in the right ballpark, by using these paleoclimate analogs. And people do more quantitative comparisons between what they call paleoclimate sensitivity, which is basically how much warming do you get every time you double CO2. And you can look at that in paleoclimate, you can look at it in climate models. You can sort of look at it from the observational record, but that's complicated because you have a short observational record, and also the feedbacks are all operating at different amounts today than they were in the peak of the ice age or 100 years in the future. Just because you have a different amount of ice, you have different amounts of methane that can give a different amount of feedback.
Yeah. Well, and also to my knowledge, those climate sensitivity numbers haven't really changed over the past 30 or 40 years. And that's not, I think a lot of people, I've seen a lot of people look at that and say, oh, that means that you haven't gained understanding. But to turn that on its head, it's more like, no, we've got a robust understanding, and we've looked at it through modern climate models with a lot of bells and whistles, very basic climate models, theoretical calculations, extrapolating observations, and we still have a pretty solid, persistent number on that climate sensitivity.
Yeah, I do think it's getting a little bit refined. Like, there's some recent work has sort of started to refine it, I think. So people have started to roll out the really low values, the lowest we have of climate sensitivities of like 1.5 degrees Celsius, or what's that, like 3-ish degrees Fahrenheit. Those have started to be rolled out just because all of those estimates, or most of those estimates, come from the modern observational record, where you directly try and look at the feedback on like interannual timescales and try and assume, you assume that those are the similar types of feedbacks that happen on longer timescales. The problem is that we think that the feedbacks actually increase with time. So things like the methane permafrost feedback, like that has barely just started, and it's going to get a lot stronger. Some types of Arctic amplification are going to get stronger. And yeah, I'm sure there's others that I'm forgetting right now. But then, yeah, and most of the uncertainty in these calculations, especially the climate model ones, comes from the effects of clouds. So we don't really know if clouds are going to act to warm the climate or change the climate.
Yeah, that seems like the biggest term right now in terms of dealing with uncertainty is getting, clouds reasonably represented in models, and rather reasonably parameterized, because we'd have to make the raw climate model resolution so fine just to be able to, explicitly represent most clouds. So
Yeah.
I guess it's that better parameterizing, but that's a little jargony, so.
Yeah. Well, so people have climate models where you can explicitly, here, I've got full pots for you, really.
Okay.
People have climate models where you can explicitly basically represent clouds. So you're literally
you nest a cloud model inside the grid cell, right?
No. I mean,
like
you can
that.
do a fully resolving the clouds on the whole planet, but you can only run it for like a week.
Oh, okay.
But you can get some
Sure.
interesting statistics from those, and I think it sort of
For sure.
hints at the
Yeah.
fact that it might be possible to do some of those simulations, or at least get something out of them. But I think, yeah, maybe what's interesting is to break down just why clouds are so hard. And there's a few reasons, and I don't really specialize in clouds, so I'll probably butcher some of this.
Sure.
But let's just cover a few of the ways. So one of the ways that clouds can change is basically if you have more clouds, clouds are reflective, and so they can reflect more solar radiation back to space, and that's a direct cooling effect. There's also a radiative effect because clouds contain water vapor, and so water vapor is a greenhouse gas, so it acts as a warming effect. Then there are some indirect effects, which are basically things that I don't really understand very well, but they have to do with how clouds interact with aerosols. And so if you put basically more air pollution in the air, that changes the way that clouds form. It can change basically the height that they form or the temperatures they form at, and it can change the types of clouds they make, or the types of basically the size of the airdrop or the water droplets. So clouds are just a huge collection of tiny little droplets of water. And it turns out that the amount of solar radiation that these clouds reflect has a lot to do with exactly the shape of these tiny little water droplets. So I think, hopefully I get this the right direction. I think if you have a lot more water droplets of smaller sizes, that actually makes a more reflective cloud, and so it would be a cooling effect.
Yeah, we talked about this in my radiation class, but I'm very likely to get it mixed up. So.
Yeah, I haven't even taken my radiation class yet.
Oh man.
We just got
All right,
wrecked.
Brian, save the day.
Yeah, Brian, this is all you.
Watch her come in on the cell phone.
There's only 4 of them.
I don't really think this is gonna go well.
Just start shooting. Start shooting now.
Okay, I got this.
He's, for our viewers, he's on a cell phone. This makes it much more difficult.